let us take a look at the next problem, which is again very commonplace problem of dimensionality reduction. Very typical with data science use cases, statistical use cases as well, right? And when we think of dimensionality reduction, you will straight away think of principal component factor models. How do these work? How are these estimated? And what is the main intuition behind using these models, right? So we looked at the regression model, we looked at various independent variables that are part of regression model. We saw that you cannot have an independent variable that is linear combination of other variables, right? So what we do is when we have very high correlation systems where one variable can be written as linear combination of other variables, we will omit some of the variables. By our own choice, we will keep those variables out of the model, right? But is that the only way of manual selection to really proceed? The way to proceed would be to use other techniques which will automatically handle the highly correlated systems, right? What essentially happens when you have a high correlation among a set of independent variables, right? And why exactly realistically we have situations where X variables are highly correlated, right? Many setups actually require or entail a high correlation among set of independent variables. Let's think of market research data, and you are interested in measuring trust in a given brand. Now you wouldn't want to ask just one question to measure trust. The question may be interpreted very differently by different respondents. So market researchers will typically ask multiple questions to measure the same trust that they are interested in measuring about their brand, right? So when you have several questions that are asked about the same underlying construct, the correlation is built in the system itself, right? So that's one setup where automatically or purposefully we built in sort of correlation in the independent variables in my analysis. The second setup would be you have, let's say, hundreds if not thousands of variables, and you are interested in using all the information that's there with these variables in your models. You may not actually know which of these variables are correlated or not correlated. So the correlation may already be existing, and you can be made aware of using some correlation analysis. But again, which of these variables to retain is not so much a choice that is defined by the domain. Think of an image kind of data. You have, let's say, even the smallest pixel size, let's say 28 by 28. If each pixel were to represent a feature of an image, you have 784 variables for an image, right? Now, which of these variables to retain? No domain expert will be able to say that these are the features you must retain. So we must be able to build model with, let's say, 784 variables. That's going to take a really long time. But can we represent this whole information that's there with 784 pixels with a smaller dimensional data? And that's the key problem of dimensionality reduction. You have many variables, many features in your model. You want to represent them with fewer features and still retain the variation that is brought in by these different variables to a greatest extent.